In this video, we're going to talk about one-sided limits. In order for a limit to exist, the value of the function, the y value, has to approach the same value from each side. Well, what if they don't approach the same value from each side? What if they approach one value from the left and one value from the right? That's where the idea of one-sided limits comes in. So this notation, the limit of f of x as x approaches c, but there's a superscript of a minus up there, that indicates that we're talking about values of x less than c. And so we're talking about, in this case, the limit from the left. Now, if we want to talk about the limit from the right, then we're talking about values of x bigger than c, on the right side of c. And so we use this notation where we have a superscript of plus on the c. So the plus again indicates we're talking about values of x bigger than c, the minus indicates we're talking about values of x smaller than c. Alright, let's look at some examples. Find the limit of f of x as x approaches 3 from the left, and the limit of f of x as x approaches 3 from the right, for each of the functions below. Well, first we've got a function that is graphed, and the squares are supposed to be of size 1 by 1, and so x equals 3 is right here. So if we want to find the limit as x approaches 3 from the left, we are talking about from this direction, so on the left side of 3. In that case, the y values are headed toward 2, and the limit as x approaches 3 from the right of f of x, so that's from this direction, that would be 5. Because as we approach 3 from the right, the y values are headed toward 5. Now here is one that we're going to need to look at analytically. You've got f of x defined to be 3x plus 1 for x is bigger than 3, and x squared plus 4 for x is less than 3. So this is what we call a piecewise defined function. The definition for the function is different depending on which values of x you're talking about. So if we want the limit as x approaches 3 from the left of f of x, remember what that definition of the limit from the left means. It means we're talking about values of x less than 3, and if we're talking about values of x less than 3, we're going to be using that definition. And I believe that's going to be 13. And if we're talking about the limit as x approaches 3 from the right, that means we're talking about values of x bigger than 3, and so we're going to be using this definition. And in this case, I think we're getting 10. Now, since these do not match, we would say the limit as x approaches 3 of f of x does not exist. The one-sided limits exist, but the two-sided limit does not. Next, let's talk about a function which may be new to you, a function called the greatest integer function, or the floor function. There are a couple of different notations for this function. One is this notation, and then another notation would be something sort of like square brackets, but these are both notations for the greatest integer function. And so the greatest integer function, or floor, of the number x is defined to be the greatest integer less than or equal to x. So you can think of it this way. If you're talking about an integer, then the floor of any integer is just that integer itself. So for instance, the floor of 5 is 5, because that's the largest integer less than or equal to 5. Or the greatest integer of negative 3 is negative 3, because that's the largest integer less than or equal to negative 3. But I've got some more examples for us to look at, and then I've got a couple of limits for us to look at. So let's look at example A. You've got the floor of 2.7. So what you're supposed to do is round down to the nearest integer if you're not already at an integer. So in this case, this would be 2. The floor of 2 would be 2 as well, right? And now the floor of negative 2.7. Be careful, the answer is not negative 2, because negative 2 is actually larger than negative 2.7, right? It's to the right of negative 2.7 on the number line. So what you've got to do is round down to the left, which would be, that'll give us an answer of negative 3. Alright, let's look at a couple of examples of limits involving the floor function. So in part D, you've got the limit of the floor of 3x as x approaches 5 from the right. And I'm going to focus. There we go. So what you need to do here is think about what this notation means. Remember, we're looking at the limit as x approaches 5 from the right. That means we're talking about values of x that are very slightly larger than 5. right, we're not talking about numbers like 28. We're not even talking about numbers like 6. We want something that's close to 5, but slightly bigger. So what you're going to do is think of values of x that are very slightly bigger than 5, and then what you're going to do is you're going to multiply those numbers by 3 and then take the floor. So you're working your way from the inside out. Did you get the answer 15? How do we get 15? Well, again, we're thinking about a number slightly larger than 5. Well, if you multiply that number by 3, it's going to be slightly larger than 15. Now, I'm being kind of sloppy. I'm not really defining what I mean by slightly larger, but I'm hoping that you can sort of intuitively gather what it is I'm saying. So 3x is going to be slightly larger than 15. Then you take the floor, you're going to get 15. Now, what about the limit from the right? Sorry, the limit from the left. At 5. All right, so remember what that means. We want a number that's slightly less than 5. So think of numbers that are slightly less than 5, then you've got to multiply by 3, and then you've got to take the floor. Well, if you're talking about a number that's slightly less than 5, when you multiply it by 3, you're going to get a result that is slightly less than 15. And then when you take the floor, remember that we're talking about a number that's only slightly less than 15, and so that's going to be 14. Let's do one more example like this. We'll call this example F. Let's do this. The limit as x approaches 5 from the left of 3 times the floor of x. I'll separate that like this. So the notation here is a little bit different. The order of operations that you're going to perform are a little bit different. You're going to take the floor before you multiply by 3 in this case. Did you get 12? X is going to be slightly less than 5, so when you take the floor, you're going to get 4. And then you multiply by 3, and you get 12. Alright, in the next video we're going to talk about functions which are continuous on closed intervals, and we'll have to twist our definition of continuity on an open interval around a little bit to include the endpoints. We'll do that with one-sided limits.